Hello. Good morning. Am I audible?
Yes, sir.
Yeah, fine. So I think screen is also visible to you.
Yes, sir.
Yeah, fine. So last class we were discussing some numericals on pulse code modulation, and also we discussed DPCM. Now I think some of you had asked what are the waveforms at each level. So we have input signal, analog input signal, both time continuous as well as amplitude continuous. And we sample it, we get discrete samples. The time is going to be discrete, the amplitude is still continuous. We're going to get the samples. So this is a discrete time signal. So you quantize the samples. Okay, so you can take samples, quantize it to some levels, depends upon what is your step size, what is the quantization. And the quantization levels you are going to assign. Say if it is 4 volts, you are going to assign 100. If it is 7, it is 111. That way you are able to assign the different codes, depends upon how many bits required to represent the quantization level. So here in this case, because the voltage amplitudes are all less than 7 volts, so you can use 3 bits to represent 0 to 7. So 3 bits are sufficient to represent all the 8 levels. Okay. So then encoding is basically you are using a waveform, a rectangular waveform. If it is 100, so 100, then 110 means 110. So some kind of a format you are going to use. Either it is called as unipolar or polar. We'll see later what is polar, what is unipolar. Unipolar means only one level. So 1 means it is plus 5 volts, 0 means 0 only. Okay, right now they have used unipolar here. And later from this digital data, that is encoded data, it is passed through digital to analog converter, then passes through low pass filter, and you are able to reconstruct approximately what was the transmitted signal. So you can see that it is without any noise. In this case, they are not considering any noise. So if noise is there, then it will be an estimate of the transmitted signal. But the shapes will be approximately same. They won't be accurately valid in the presence of noise. So now also how the PCM and DPCM looks like. Okay. The PCM is basically you are taking the samples, quantizing each sample. You're going to quantize each sample value to the level. You can see that here. So there are samples. Okay, say this sample, first sample is quantized to 101. Second sample is quantized to 100. Third and fourth sample are quantized to 011. So like that, each sample is quantized to some level in PCM. Okay, so this digitized PCM means pulse code modulation. We have done the sampling, quantization, then encoding is going to be, we're going to take each sample, quantize it, and assign different code words. That is PCM, pulse code modulation. In DPCM, so we oversample the signal, we increase the sampling rate to far greater than 2 FM, so that the correlation between the samples is very high, and we take the difference in the sample values. Okay, so then the difference in the sample values is quantized. That is called as differential pulse code modulation. So each sample is quantized in PCM. So here the difference in the sample is quantized in DPCM. The waveform, you can see that in PCM, if you want, if you are representing the quantized levels with the different voltage levels, and when you quantize it, we are requiring a 3-bit quantizer. Okay, so 8 levels are there. We need 3 bits to represent 8 levels. But in DPCM, because we are quantizing the difference value, not the samples itself, so that is why you need only 4 representation levels, and only 2 bits are required to represent this. So the implementation wise, I think we have seen yesterday. The implementation wise also we have seen. You can see that complexity increases. Okay, but remember the transmission bandwidth. Okay, is very small bandwidth is required for DPCM, but complexity will increase in DPCM. Please compare to standard pulse code modulation. So you can see only 2 levels are required to represent, but we need to do the prediction. Okay, so system complexity is more, and transmission bandwidth is lesser. So we need only 2 bits to represent the 4 levels. Okay. So is this clear to you how the waveform looks like in DPCM and PCM?
Yes, sir.
Yeah. Others?
Yes, sir.
Okay, fine. So also we were discussing numerical part yesterday, and let me clarify this in the textbook notation. Okay, so according to the textbook notation, it is actually kilo samples per second. It is given here as kilobits per second. This has to be kilo samples per second, then it would be correct. So this is kilo samples per second, and we have 16 bits here. So 44.1 kilo samples per second into 16 bit per sample. Okay, 16 bits per sample. So sample can cancel. You can have bits per second. Okay, so that way it is proper. So this is samples per second. So in a reading, maybe the author meant is 44.1 kilo samples per second into 16 bits per sample. Okay, 16 bits per sample. So sample you can cancel, and it will be bits per second will be the data. So is this notation clear now? Hello?
Yes, it's clear.
Okay. Fine. So that is, I think, notation textbook we need to understand. The author meant like that. That's fine. So now let us continue this. And mu is equal to 255, or let us say 256 quantization levels are required. 256 quantizing levels are used. Okay. Now, what is the voltage between the levels when there is no compression? What is the voltage between the levels when there is no compression? That means uniform quantization. When there is no compression. Okay. Next is when mu is equal to 255. We are applying mu law in non-uniform quantizer. What is the smallest? What is the smallest and what is the largest effective separation between levels? Okay, so this is what we need to do. So we will not plot it now, just we can take the waveform and understand from the waveform. So let me take this waveform. So what you need to do is, there are...
Can you show the parts again?
Yeah. Plot mu law compression for mu is equal to 255. Okay, maximum value for mu is equal to 255. Then next is the input signal peak amplitude is given 20 volts and 256 levels are used. So 256 levels means n will be 8 bit, 8-bit quantizer. Okay, so now before plotting, what you need to do is, first we need to compress this. That is, you need to normalize this. So m by mp. Okay, so you need to normalize this value so that this x will be 1. I think we mapped all the values from -1 to 1, right? So that way we need to map all the values from -1 to 1, normalize and compress these values. Okay, so you can see now when you plot the mu value, okay, mu for 256 levels, quantizing levels, and map it, and it is between -1 to 1. So you can see that it is all the lower amplitude levels are quantized. Okay, more levels here, and higher amplitudes with lower quantization levels. Okay. I mean, few levels are required to represent higher amplitude levels, and more number of levels are required to represent lower amplitude levels. Okay, so this is that, and between the levels when there is no compression. So voltage between the levels means it will be 0.156 volts. Okay, so this will be the voltage between the levels or step size. Okay, so voltage when no compression is used, the step size we need to find out, voltage between the levels. So this will be 0.156 volts. And next in this only, when compression is used, you can read that. This is when mu is equal to what is the smallest and what is the largest effective separation between the levels. So we need to find out what is when two utilities. So if you consider this graph, okay. So when it is y is equal to, say, this is actually 256 means 127 to minus 127, okay, in moles.